Hello everyone, in this video we'll discuss about forced vibrations. Now forced vibrations, they are basically the result of continuous external force which is being applied on the system, and it is different from the natural vibrations where the force is applied once and the system is left to vibrate on its own freely. So assemblies of the components or structures, they sometimes fail even against the mild forced vibrations, right? Therefore, it is very important to study the forced vibrations and their effect on the system. So now we say in forced vibrations, we are giving some external agent or some external excitation to the body or to the mass. So the excitation given to the body or the external force given to the body, it can be classified into three categories. First one is the periodic excitation. What we mean by periodic excitation, that means the cycle, it repeats itself after certain duration of time. Again, periodic can be classified into two categories. One is the sinusoidal, right, which follows the sine curve, and the other one which is periodic but it does not follow the sine curve, sine or cos curve, right? It's not sinusoidal. So the second one is non-sinusoidal, which is periodic. That means the cycle is repeating itself after certain fixed duration of time. The non-periodic ones are the ones which do not repeat itself after certain or fixed durations of time, and the random ones are totally random. We cannot tell about them that what type of motion will be there or what type of excitation will be there to the system. Now these excitations can also be categorized as the force excitations, base excitations, or the self excitations, or the parametric excitations, right? So in this video we'll talk about the forced excitation or the forced, which external force is being applied on the system, and we'll use the case of the periodic and sinusoidal force vibration in this particular video. So let's assume a system, right, a mass m, which is attached to a spring of spring stiffness S. Now if a force, a constant force Ft would have been applied on the system, causing displacement about its equilibrium position, so the equation, the general equation of motion would have been this, where mass into acceleration, which is mx double dot plus the spring force, it would have been equal to the force applied, the constant force which would have been applied. But we are saying that in case of the forced vibrations, instead of applying a constant force, we are applying a harmonic force, which we are denoting by this equation, by this value, which is F naught cos omega t, where F naught is the amplitude of the force and omega is the frequency, right? So now the equation becomes, if we see the free body diagram, so the force, the external force is this, acting in the direction of the velocity or the displacement of the mass, and the spring force, it acts in the opposite direction. So the equation looks like this, that the movement of the body is in this direction, so mass into acceleration is equal to F naught cos omega t minus the spring force. So we can write this equation in this way, right? Now this equation, if you look at this equation, it comprises of two components. The first one, this is because of the SHM, and this is because of the dynamic force which is being applied on the system. Therefore, the general solution of this equation, it also comprises of two parts. One is the complementary function, which is because of this part, the SHM part, and the second one is the particular integral function, which is because of this dynamic component of force, right? So the general solution of equation will be like this: x is equal to a sine omega nt plus b cos omega nt. This we have already discussed, which is the general equation for this part, plus it comprises of the second component, which is f naught upon s 1 minus omega upon omega n square into cos omega t, which is because of this dynamic force, right? So if this is the value of x, So we can also write this equation in this way, where omega upon omega n is known as the frequency ratio, and it is denoted by small r. So we can replace omega upon omega n with r. So this is the first equation. Now if this is the equation for displacement, the equation for velocity will be this omega n a, that is the natural frequency, into amplitude. So sine will become cos omega nt minus cos omega nt will make minus omega n sine omega nt, and the differentiation of this cos omega t again will give minus omega sine omega t. So this is the equation for the velocity. Now with the help of these two equations, we'll find the value of the constants a and b. So we'll use the initial conditions. The initial condition says that at time is equal to 0, the displacement is also 0 and velocity is also 0, because at time 0 the force applied is 0, therefore displacement and velocity both are 0. So if we place these values in equation first and second, we find the value of two constants, right? So sine 0 is 0. So from equation 1 we get the value of b. So b becomes minus f naught upon s 1 minus r square. And in third equation we get this factor, which is a cos omega nt. So omega n, right? Okay, omega n into a, because time is 0, so it becomes 0. So a also becomes 0. That means the only constant we'll be using further is b. So now if we place the values of the constants that we have found, a and b, in the equation of displacement, we find it to be f naught upon s 1 minus r square cos omega t minus cos omega n t. Now if we use the trigonometric function, we can rewrite this equation as this, which is sine omega n plus omega upon 2 into t sine omega n minus omega upon 2 into t. So in this equation, we see that in cases when omega is slightly less than omega n, we get the positive amplitude and vice versa. Now this phenomena is basically showing a beating phenomena, right? Beating phenomena means that the cases where omega, or the forcing frequency, is very close to the natural frequency. They are of course not equal to each other, but they are very close to each other. So what happens? The amplitude, right? It builds up and it diminishes. So basically it is following a regular pattern, and this time period is denoted by the 2 pi omega upon omega n, is called as the period of beating. Now if we go to a condition where omega is actually equal to omega n, or it's very close to omega n, that the frequency ratio is 1, so what happens? This factor f naught upon s 1 minus r square, it becomes infinite. That means the amplitude becomes infinite. Means what? The amplitude, it increases, right? Exponentially it increases, and of course it is not going to reduce or decay, but what it will cause, now it cannot reach the infinity value. It can reach up to a certain value, and beyond which the machine will damage or it will break. So when omega is equal to omega n, or when it approaches omega n, then what we get? We get the condition of resonance. So the study of forced vibration system is very important, because they actually help us in predicting the behavior or the response of a structure or any mechanical system when it is subjected to some external force. Let's take an example that if we want to design a bridge, right, and if we want to find out the response of the bridge, or maybe a tall building, right, or maybe the earthquakes, or let's say because of traffic, whatever ground vibrations are there. So what we want to find out? We want to find out that when external force is acting on the system, how it will behave. If I'm designing a bridge, right, we have to see that what will be the footfall, and how much external force, what type of force is applied on the system, and its response. So whether we are designing a suspension system, or maybe a bridge, or maybe the any building, or maybe we are discussing about the wind loading or the earthquake. So the force vibrations are very important. And two terms that we have already discussed, but again I'm telling, are the transient and the steady state. So whenever we are solving these equations, we are interested in the steady state response of the system. So basically this is the response of the forced damped system. And the steady state, you have already seen the equation that it is independent of the initial position and velocity of the mass. And if the force is a harmonic function, the steady state response will also be the harmonic function of the frequency of the force. But of course, it may have some phase lag depending upon the frequency of excitation and the properties of the system that we are considering. And what is the transient state? Transient state is the state between which shows the behavior of the system while it is approaching the steady state, right? So this transient state, it is very short lived. It is only for short duration of time because of the because of the free vibrations in the system. So we usually do not take into consideration the transient state. We are more concerned about the steady state response of the system. So now we'll see the forced vibrations due to support motion. Now what does it mean? It means that when the base of any spring is given some motion. So what will happen? That motion, it causes the vibration in the mass or in the system. And this concept can be used while designing the suspension of a vehicle or the earthquake response of any structure. Or maybe we can take the example of, let's say there is some offshore structure, and when some wave loading is there, the waves are applying the some motion on the the base of the system or the support of the system, and the system vibrates. That is the response or the behavior of the system that we need to study. Now, if we take a mass, right, it is having the displacement from its equilibrium position in this direction. So let this be in terms of x, which is a function of time t. It is attached to a spring of spring stiffness S and a damper with damping coefficient C. Now, what is the condition? The condition says that some motion is given to the base, and because of this, the vibration is happening in the system. So let the motion given to the base be y in terms of y, which is a harmonic function. So let it be y sine omega t. And if this is the motion provided to the base, so this is basically the displacement, right? So the velocity will become y omega cos omega t. Now if we draw the free body diagram of this mass, so the motion is taking place in this direction, which is m into x double dot, right? And this force is equal to what? The restoring force, which is acting in the opposite direction, and the damping force, which is also acting in the opposite direction or towards the fixed end. But we know what is this restoring force of spring. It is spring stiffness into displacement. Now what is the displacement of the spring? This is basically the relative displacement, because the mass, it is having the displacement x, right? And the motion provided, the external displacement provided is y. So the relative displacement becomes x minus y. Similarly, the relative velocity becomes x dot minus y dot. So this is the damping force which is acting in this direction, right? So if we apply the Newton's second law, this is the equation that we get, right? Basically what we are doing, we are balancing the forces. We say that the system is in equilibrium, so the forces acting on in this direction, they are balancing the forces so acting on the opposite direction, right? And we've used the negative sign because the direction of these forces is opposite. So this is the equation that we get, right? Now we know that x is the displacement of mass and y is the displacement of the base. So what we can do is we can take all the factors of x on one hand and all the factors of y on right hand side, right? Now we have already discussed that y is a harmonic function, so we can replace this y with y sine omega t and y dot with y omega cos omega t. So this is how the equation looks like. That means if we draw the the graphical representation, so this is y at some frequency, that is omega t, and this is the velocity, which is y dash, right? Now if we take this, now what is y? This is because of these, this is c into omega, right? If we talk about the maximum value of this component, it will be c omega, and the maximum value of this component, which is s sine omega t, will be s. So if I plot the vector diagrams, it will be something like this: s in the direction of y and c omega in the direction of y dot. And this we have already discussed that while plotting these diagrams, if you look at these trigonometric function, so y dot will be y omega sine omega t plus 90 degree, right? So this is how the equation looks like. So if I plot the vector diagram, so it will be c omega, right? And let the resultant of these forces, because if you see on the base, the forces that are acting are the spring force and the damping force, right? If I take the individual this y component, so let the resultant of this s and c omega be a factor k, and this angle be alpha, right? So if I want to find k sine alpha, that is c omega, and k cos alpha is s, right? So we can replace s and c omega in this equation, so this becomes the equation. So we are not touching any x factor. What we have done, we have just replaced c omega and s with the values that we calculated here, right? Now we can also find the value of tan alpha. So tan is what? Sine alpha upon cos alpha. So it becomes tan inverse c omega upon s. So this is the value of alpha, or the angle. Now if you look at this equation, it can be written as y into k. We take k common. So this is the trigonometric function. So we can write it as sine omega t plus alpha, right? So let's say sine omega t plus alpha is some angle alpha, some angle, whatever is the angle alpha for this resultant, that is k, right? So let's say k is acting in this direction, some direction like this. So this angle is alpha. Now we have already discussed, now this equation now you see comprises of two components, the steady state component and a transient component. So the steady state solution for x, it looks like this, right? Which is y into k sine omega t plus alpha and minus phi, where phi is what? The phase lag, and under root s minus m omega square whole square plus c omega square, right? Now, if you remember the graphical analysis that we have already done for this equation, which is mx double dot plus cx dot plus sx. So what was the value that we were getting? And if we are assuming that xxt is equal to x cos omega t minus phi, that means there is some phase lag between the displacement and the force that is being applied. So if you remember this diagram, so this sx at some angle, right, omega t, and c omega x, which is in the direction of this velocity, and the this in the direction of acceleration, we have got this force, which is m omega square x, and the resultant, which is denoted by f naught. So this was the equation that we were getting, that this xt, right, this is the axis of xt, and the axis of force, this is force, right? So the angle that they are making is, if this angle, whole angle is omega t, and this angle is phi, because we are describing the angle for the force, so it becomes x cos omega t minus phi. And to find the amplitude for the steady state equation, right? Because the steady state equation, it is independent of the displacement and the velocity of the system. So x was given by this factor, which was this. So for finding this value, what we have done, we have made a construction and made a line perpendicular on Sx. So we want to find the magnitude of f naught. It will be what? Because this is a right angle triangle, let this be, let's say A, B and C. So we can find the value of AB, which can be written in this form. So we can find the value of the amplitude, which is x. So the same concept we have used here. So for this equation, the general solution that we get is this, right? That we have already discussed. Now what we are doing is, we want to find the amplitude of this equation. Now amplitude is for the steady state equation, and it is independent upon the velocity or the the initial position of the system. So this factor will not be taken into consideration, the harmonic function. So this is the amplitude, right? Can I write this equation as A upon Y? So this is the equation that we get, right? And what is K? K we have already discussed is the factor, this factor, right? Because if K is the resultant, it is what? Under root C square omega square plus S square. So we'll replace K with this function, right? Now we already know that omega n, which is the natural frequency, is under root S upon M. So we can write as S as what? M into omega n square, right? And we also know that the damping factor zeta is what? C upon Cc. So we can also replace this C, the damping coefficient, with zeta into the value of Cc. And this is how the equation looks like, right? Now, the angle phi for this equation will be what? Phi will be this tan inverse 2 zeta omega upon omega n upon 1 minus omega upon omega n whole square. This we have already discussed multiple times, because this is what? This is the sine factor and this is the cos factor. So we can find the value of tan inverse. We can find the value of phi, which is tan inverse of this factor. But in this case, you see the phase lag is what? Alpha minus phi, right? That means you have to find the difference between phi and alpha. So we already know the value of phi. And what will be alpha if I want to find phi minus alpha? Alpha we have already discussed is this, tan inverse C upon omega. So, sorry, C omega upon S. And we know S is what? M omega n square. So we can replace the values, and this is the equation we get, which is for phi minus alpha. So this equation tells, right, if we look at this equation which is A upon Y, and this equation, so if we look at the ratio of A upon Y, we'll see that when the frequency of the system, that means omega, it is very small to the natural frequency. So what will happen? If omega is very small, this factor A upon Y, it will become 1. That means the complete system, it will start vibrating like a rigid body. And in case when omega is very large than omega n, then we'll see that omega upon omega n, it will approach infinity and the body will become stationary. There will be no movement in the body because A upon Y, it approaches the value 0. So this factor A upon Y, it can also be termed as the displacement or amplitude transmissibility. We can also solve this equation by using the relative amplitude method, right? Till now we have already discussed, right? So we say if you saw the free body diagram, the relative displacement is x minus y. So can we write x minus y as z? So x will become z plus y, right? And we already know that y is a harmonic function of sine. So y is what? Y sine omega t. So we can find the value of velocity y dot and the acceleration, which is y double dot. So if we use these five values and change the equation 1, so it becomes m x double dot is what? Z double dot plus y double dot plus c into x dot minus y dot. So x minus y is z, so x dot minus y dot becomes z dot plus s into x minus y, which is z. So this is the equation. Now we open this bracket and take the y factor on the other side. So the equation becomes this, which is mz double dot plus c del z dot plus sz is equal to minus m y double dot. And what is y double dot? This. So minus minus becomes plus. So we get the value, which is my omega square sine omega t. So similarly, like we solved it for x, we can solve the equation for z and we get the ratio z upon y. The value remains the same, which is omega upon omega n whole square under root 1 minus omega upon omega square whole square plus 2 zeta omega upon omega n square. So what is z? Z is actually the steady state relative amplitude. Earlier we were talking about the amplitude of the mass or for the body, but if this is the ratio for the relative amplitude of the system. And the phase lag, the phase angle, if we want to find, the equation remains the same as it was in the earlier condition.